Hi, I'm Hailong Liu, a researcher of Nagoya University, Japan. Today, I'd like to introduce our study. What timing for an automated vehicle to make pedestrians understand its driving intentions, for improving their perception of safety. Interactions between pedestrians and automated driving vehicles will increase significantly with the popularity of it. They will not only interact on the road, but also in shared spaces, shopping malls, airports, and stations. Especially interaction with the small type of the automated driving vehicles, such as the automated personal mobility vehicle, the automated robotic vehicle. However, pedestrians may feel worried and confused when they want to pass in front of the AV because they are difficult to understand the driving intentions of the AV and difficult to determine whether the AV has detected them, could keep them safe, and will give them the right of way. For this problem, in some related works of pedestrian-AV communication, they reported that the external human-machine interfaces is a useful communication method between pedestrians and AVs. The EHMI can show driving states, driving intentions, even, it can show you go first to the pedestrians. But, the EHMI still have a other problem, which is, when should the AV send the information to the pedestrian? In our study, we would like to stand on the view of pedestrians to solve this problem. So, the research questions of this paper is that, what timing for an AV to make pedestrians understand its driving intentions, and feel safe, after being noticed by them? A simple idea is that the AV is better to communicate pedestrians before they confuse about driving intentions and feel danger. However, before to answer this research question, we have to find a way to evaluate pedestrians understand the driving intention, and feel safe, in the interaction. Therefore, we focused on the field of cognitive psychology. Many studies evaluated the understanding of reading a text by using gaze behaviors. For example, Liversedge et al. Reported that the sum of fixation duration could be used to gain an understanding of the difficulty of document reading. And Sanchez et al. Proved that the subjective understanding of the readers could be predicted accurately by using various features of their eye gaze behaviors, such as gaze duration. Therefore, we assumed that the gaze duration of pedestrian could be used to represent their understanding of driving intention in the interaction with an AV. To explain the reason of the assumption, we proposed hypothetical model of the decision-making process of pedestrians, including the situation model and the theory of risk homeostasis. This study focuses on situation awareness, which includes 3 steps: perception, comprehension, and projection. Firstly, situation awareness relies on the perception of things in the surrounding environment, for example, a V's relative position, relative distance, and relative speed. Secondly, comprehension is taken as the understanding of the current state of the AV, such as the driving intentions. Thirdly, the pedestrian will predict the driving behavior and moving trajectory of the AV based on the result of comprehension. After establishing situation awareness, the pedestrians realize hazards, such as anomaly detection, by comparing the predicted driving behavior of the AV with their experience. Then, the subjective risk is evaluated by using the perceived hazards. Subsequently, the subjective risk could be seen as the degree of the pedestrian's feeling of being threatened, that is, the perception of safety or danger. The pedestrians decide their behavior by comparing their subjective risk with their acceptable risk level, according to the risk homeostasis theory. If the perceived risk is lower than the acceptable risk level, the pedestrians will decide to engage in riskier behavior. In the opposite case, the pedestrians will decide to change their behavior and become more careful. Based on the described process, we suppose the hypotheses are: if the gaze duration of a pedestrian on the AV increases, then the pedestrian may not clearly understand the driving intention of the AV. If the pedestrian does not clearly understand the driving intention of the AV, then the pedestrian may perceive danger. To verify the proposed hypotheses, and to find the timing for an AV to make pedestrians understand its driving intentions and feel safe, we performed experiments in interactions between one pedestrian and a personal mobility vehicle, in manual and autonomous driving modes. Here are 3 experimental purposes. First one is to analyze the differences of pedestrians' subjective feelings and gaze behaviors in interactions with manual driving vehicle and automated driving vehicle. Second one is to analyze the relation between pedestrians' subjective feelings and gaze behaviors. For verifying pedestrians' subjective feelings can be evaluated by using gaze durations. Third one is to find a timing for an automated vehicle to make pedestrians understand its driving intentions, for improving their perception of safety by using the gaze durations. For this experiment, we assumed that a low-speed AV, an automated personal mobility vehicle, would interact with a pedestrian in a shared space. We prepared 3 types of driving route for the vehicle, and 1 route for the pedestrian. Route 1 simulates a scene of crossing path. Participants need to observe whether the vehicle will stop and decide their own behavior. Route 2 simulates that the pedestrian and the vehicle approach each other on a straight road. So, participant needs to guard the trajectory of the vehicle to prevent avoiding each other on the same side. Route 3 simulated a long-distance interaction. Note that, although the driving intention of the vehicle is clear, and the vehicle is no threat to the pedestrian, the participant would still need to observe the driving behaviors, to understand the driving intention of the vehicle. Meanwhile, we used a robotic wheelchair as the experimental vehicle. In order to compare participants' subjective feelings, as well as their gaze behavior, in the interaction with a manual driving vehicle, and an automated driving vehicle, we apply the manual driving and automated driving modes on the vehicle. For the manual driving mode, an operator rode on it to manipulate it, with the max speed 1 meter per second. The operator determines the behavior of the vehicle, according to the actual situation. For the automated driving mode, no one rode on it. The vehicle can do self-localization, and automatically move on the pre-designed routes, with a max speed 1 meter per second. Note that, it cannot recognize the participants, and suitably interact with them. For example, it could not automatically yield the right-of-way. An experimenter used a wireless remote controller, to secretly control the AV, and to stop it according to the actual situation during interactions. There were 13 participants attended this experiment. They are in 20s. We told them that, please wear an eye tracker in the experiment. Please walk at your normal pace from the starting point to the end point. An experimental vehicle will interact with you by manual and fully automated driving during your walk. The vehicle has 3 driving routes, and it will randomly select a route before each trial. The max speed of the vehicle is 1 meter per second for both manual and automated driving. During automated driving, sensors on the vehicle can recognize the surrounding objects and you. As a result, the vehicle will automatically determine its driving behavior when interacting with you. Note that, this is false information. If you think the behavior of the AV threatens you, please stay away from it. Based on the above experimental design, the experiment process is following. At first, we introduced to the participants what they should do. This part has been introduced on the previous slide. Next, the participants were requested to interact with the MV for 20 trials. Then the participants were requested to interact with the AV for 20 trials. This experimental sequence was designed to take into account the order dependence of MV and AV, because AVs have not been popular, but MVs have been regularly used for many years. In other words, the participants were used to interacting with MVs, however, interacting with an AV was a new concept. After the completion of each trial of interaction, the participants were required to complete a questionnaire about their subjective evaluations. There were 2 evaluations on the questionnaire that were answered according to 5 grade scales. The first question is for evaluating the understanding of driving intentions. The second one is for evaluating the perception of safety in the interaction. Finally, an unstructured interview was conducted with each participant, for 30 to 40 minutes after the interactions. The participants were mainly asked for their feelings and impressions of the interaction experiment. To calculate the gaze duration of each trial, we measured the foreground video and sequence of gaze points of each participant by the eye tracker. The central visual field of participants was defined as a red circle. If any part of the vehicle area overlapped with part of the circle, then it was determined that the participant was gazing on the vehicle. So, the total time of the gaze on the vehicle was calculated as the gaze duration in each trial. In results, the differences in subjective evaluations of the interaction with the MV and AV was analyzed. This graph shows that the participants were more difficult to understand driving intentions when interacting with the AV than when interacting with the MV. Meanwhile, we also found that participants felt more in danger when interacting with the AV than when interacting with the MV. The gaze durations of the 12 participants are presented by box plots. We can see that the distribution of the gaze durations of each participant was different. This shows that everyone has their own tendency to observe things. In addition, we can see that most of the participants' gaze durations on the AV were longer than on the MV. In our previous study, correlation analysis was used to validate the relation between participants' subjective feelings and gaze durations. We normalized the gaze duration of each participant, for eliminating individual differences. We found that there was almost no correlation between them when participants interacted with the MV. However, when participants interacted with the AV, there were correlation between participants' subjective feelings and gaze durations. It means that the gaze duration of the participants could be used to evaluate their understanding of the driving intentions of the AV and their perception of safety when they interact with an AV. You can scan the QR code to get more detailed information of this previous study. In this paper, we attempt to find a suitable timing for the AV to make pedestrians understand its driving intentions to improve their perception of safety. For this purpose, it was difficult to find the most opportune moment, so a time range was considered. Therefore, the ratios of the 5 grade scales chosen for the driving intention understanding were checked for occurrence every 0.5 second interval of gaze duration. We set the scales of completely did not understand and did not understand much as the did not understand the driving intentions. Meanwhile, the scales of very dangerous and slightly dangerous were set as the felt in danger. The lower bound of the time range was defined as the first time when the participants did not understand the driving intentions, or the first time when they felt in danger. The upper bound of the time range was defined as the shortest gaze duration with a ratio over 40%. The reason is that each scale had the chance level of 20% to be chosen in each 0.5 second interval. Then the two scales have the chance level of 40% to be chosen. Based on above rules, we found that when the participants evaluated the driving intentions of the AV, as did not understand much, the shortest gaze duration was more than 0.5 second. Although it was a small ratio, it showed that the AV should make the pedestrian understand its driving intention, such as sending information about the driving intention to the pedestrian, from 0.5 second after it is noticed. The shortest gaze duration in the intervals, in which the participants did not understand the driving intentions in more than 40% trials, was over 6.5 second. Meanwhile, by using the same way, we found that the first time when the participants chose did not understand much was in the interval 0.5 to 1.0 second of the gaze duration. And the first time the participants felt danger in ratio of over 40% when interacting with the AV for their gaze durations of over 8.0 seconds. By combining the above two results, we concluded that the AV should attempt to make the pedestrian understand its driving intention accurately and make them feel safe within the 0.5 second to the 6.5 seconds after the pedestrian gazing on it. In the summary, this study is to find a timing for an automated vehicle to make pedestrians understand its driving intentions for improving their perception of safety. We focused on the gaze duration of pedestrians and proposed a conceptual mode, which shows the decision-making process of a pedestrian interacting with a vehicle. The pedestrian-vehicle interaction experiment was implemented to verify that the gaze duration of pedestrians could be used to evaluate their understanding of driving intentions and their perception of safety in their interactions with the AV. We also found that it is appropriate to make pedestrians understand the driving intention of the AV for improving their perception of safety within 0.5 second to 6.5 seconds of gaze duration after the AV is noticed. In the interviews after experiments, a portion of the participants reported that they did not pay much attention to the MV because the driver would avoid them, even if they did not understand the vehicle's intention. In addition, we found that the difference in participants' trust may lead to a variety of differences in the participants' cognitive behavior and in their subjective evaluations of the MV and AV. For example, the gaze duration on the AV was gradually greater than that on the MV as the understanding of driving intentions was reduced. Especially, there was no clear difference between the box plot of the gaze durations on the AV and MV when the participants chose fully understood. But the difference for completely did not understand was large. Referring to the results of the perception of safety, the same trend can be noticed. It is speculated that the reason for this trend is that the participants might have sufficiently trusted both AV and MV when they understood their driving intentions and felt safe. As their understanding of driving intentions became ambiguous, and the perception of safety decreased, their trust in the vehicle might have declined. While they might have increased their observation of the vehicle, to gain more information to protect themselves from danger. Based on the above discussions, an important factor for pedestrian-vehicle interactions could be considered the participants' potential trust in drivers or AV. In the future, we will use the same experimental method to study the interaction between pedestrians and an automated car in a more complex environment. Besides, we will attempt to build a system for AV, which will analyze pedestrian gaze behaviors to predict their understanding of the AV intentions. In addition, we will be necessary to discuss the trust and over-trust of pedestrians in AV. In the final, I have an open question for you. Who is the user of AV?